Welcome to Real Physics Talk. Today, my guest is Mike McCulloch from Plymouth University, and he was an oceanographer there, a real physicist in the best sense of the word, connected to reality. And he's now, well, for some time doing fundamental physics as I do. And of course, we are a little bit out of the mainstream, but this is, I guess, what will it make interesting. I should say that I very much like your general approach as a physicist because, well, you are thinking about the big picture, the very fundamental issues of physics, of which there are many, and you are connected to reality. You have written in your book about anomalies, a lot of anomalies. By the way, we will talk then in more detail about his book, Quantized Accelerations. And not only he's rooted in reality, I think he has a really good overview of physics. He's in cosmology. He talks about quantum mechanics and even thermodynamics you find here. And he thinks history is important. I guess this is one key factor if you want to look at some alternative theories. Forget about if people are ignorant about history. I think that's key. And what I also like, you work with intuition. That's very important. And it's one property that is missing in contemporary physics, I guess. So yeah, I welcome again Mike for this talk. I'm intrigued by what you have to say. And yeah, let's just start.
Well, yeah, thanks for that introduction. That's great. And I've always admired your work as well.
Mhm.
And an early inspiration for me was one of your papers on the archive. It had a title something like "Why Do We Still Believe Newton's Laws?" And you had in there many anomalies, and you tried to see patterns in them.
That was back in 2007. When I got involved in these anomalies in cosmology, right? Yeah, glad to
Yeah.
hear that.
And I liked your common sense approach and your interest in Mach and Mach's principle and his method, and also your book Einstein's Lost Key, which I read quite often. Actually, I dip into it.
Yeah, that's about the variable speed of light theory. Yeah, my field as you if you want. But well, let's talk about today about your approach. I mean, we have some little overlap, I would say. We are both convinced with, apart from the general physics stuff, but there is some overlap regarding variable speed of light, regarding explanation of the gravitational constant. At least that is something to explain, and there is something left to understand. And well, I mean, maybe I'm not endorsing everything you say, and you're not endorsing everything what I am saying, but I think that yeah, the important thing is that conventional physics is a mess. It's clearly it has gone astray, and we need some new ideas. And I think yeah, the fundamental questions you raise, and you're on a good track. So yeah, maybe, I mean, we could, there will be an index in the video so people can skip to the respective part, but maybe what motivated you, or what's your main critique of modern physics, or when did you realize for the first time that there is something more that you hear from your professors, or there is something more than we know that it is an established theory? And when did that start? That skepticism, I would be curious.
One of the important things I read was a book by Feynman. I think it's Surely You're Joking, Mr. Feynman.
Yeah, I know that. Yeah.
And in the beginning, he has a story about his father and his They were talking about inertial mass.
Yes.
His father very wisely didn't try to explain inertial mass to him. He just gave him the observation of it, what happens, and then said that nobody understands why this is true. And I love those words.
Yeah, I know. There is even a video clip. I mean, there's something I like and I dislike with Feynman. Feynman is kind of honest in admitting that there is a problem, say with inertia also. The other hand, I mean, his explanations is kind of superficial from the content. I mean, he doesn't bother with Mach's principle. He doesn't bother with the big questions of cosmology, where gravity does come from, and though that's not his business. But he, at least there is a rest of honesty and a part of a real scientist in his personality. Yeah. I got inspired a lot of, I mean, in my early student days, let's say, yeah.
Yes, me also. So I started thinking about inertia an awful lot. Where does it come from? And as you said, my background is in ocean physics. And I became fascinated by the maritime Casimir effect, which is what happens when you have two ships side by side. So the waves between the ships are damped. Only certain wavelengths can exist, but outside the ships, you can have any wavelength. This is just like the Casimir effect, of course. And
I see. I see the analogy, the waves between ships being damped, and if you bring that to the quantum vacuum, you're more or less at the Casimir effect, right? Yeah.
That's right. Yes, it's very, very similar. And so I liked that kind of explanation because you could test it all the way along. You could see the waves, you could measure them. Whereas I saw most of modern physics to be in a state that it cannot be tested. For example, the idea of curved space-time is a very fascinating one, but you can't actually measure a curve in space-time except by passing something through it, which is the reason it was invented in the first place. There's no second way to test it or direct test. So I began to think, why can't I take principles from ocean physics and apply them to general physics, and would that be more testable? And yeah, so I started thinking about inertial mass, and so I worked out a way to explain inertia that way. So if you have an object that's moving, say, to the right, if you try to picture it, then it will see a horizon to its left, because information from that part of the universe will not be able to catch up with it. So there'll be a horizon there. And I made the assumption that maybe this horizon, which comes from relativity, of course, could interact with the quantum vacuum, which is like a sea surrounding the object. So just like a ship at sea, which damps waves, maybe this horizon could damp the quantum waves behind the object in the direction opposite to its acceleration. And that would mean there'd be more waves in front of the object than behind, and they might push it back.
I remember at the end of your book, you make the analogy of applications. Maybe jumping to the end now, but you said you put a skirt on the waves on one side of the ship, damping all the incoming waves, which do not transfer momentum anymore. And then obviously you have a resulting force of the rest of the waves pushing you to the side of the skirt, right? So that would be the analogy. Yeah.
So I did the calculation properly to see if this would account for inertial mass, and it did. It looked just like what we know to be inertial mass, but with a very tiny difference. So it turns out that the inertial mass is very slightly less than we would expect for very low accelerations. But that's great, because it was just the difference we need to explain galaxy rotation without dark matter.
So just jumping back before we're going into too much of the details, I want to know about your your motivation. I mean, because it requires a lot of, I mean, also self-confidence and standing to say, okay, there is something dissatisfying with the current state of affairs, also in cosmology, also in general relativity, while a plethora of physicists is celebrating and talking enthusiastically about all the big accomplishments. I mean, where did that nagging doubt come from? I mean, if we look, I mean,
Yeah, I
if
suppose
you're talking to a young physicist who is believing his professors and so what would you say? What would you
I suppose as a person, I'm quite detached.
mhm,
So I mean, I do get along with people, but um I don't particularly believe what they say.
mhm,
And when I started all this, it wasn't part of my job. It was just a hobby, really,
mhm,
that I was doing for fun in the evenings. So I had nobody to tell me I was doing the wrong thing, perhaps.
mhm,
And yeah,
mhm. Yeah, I should say what I forgot in the introduction. I mean, what you're doing right now is not just for fun. I mean, DARPA, I guess, is funding you with a lot of money. So, I mean, even if the idea might be heterodox, it's not, I mean, they won't throw out the money for nothing. That's definitely interesting. And you have achieved at least something. I mean, considerable interest also. But I think, I mean, to be honest, it's very far out of the mainstream. So you said that you're, well, independent, have also economic independence now, but I think it's a mental independence also to begin with, right? What
yeah.
you need for, yeah, not to believe in authority. If you circle back to Feynman, that I understand. Yeah, he.
I think that's essential, really, to make a
Mhm. So you have always your thoughts have immediately been centered around the problem of inertia. Uh, that was always your focus of interest, or is this the central point? Could we say that?
I suppose it's the central point that started me off on this particular uh, journey. I mean, I've always been very interested in fundamental physics.
Mm-hmm.
When I was just out of university, I tried to publish a paper on the EPR paradox
Mm-hmm. Yeah, yeah.
to do with time, and I finally published it, kind of 20 years later, quite recently, uh, arguing that time is for quantum systems, time is porous, which helps us to explain the EPR paradox. And
Just repeat that phrase. The audio was too. Um,
yeah, so the idea is that time is porous.
mhm,
So for quantum systems, and so they can in some sense see the future,
mhm,
which is similar to some ideas of John Cramer, but
mhm,
it's
mhm.
slightly different.
Yeah. No, I like, as I said, I like your approach because it's very broad. You even consider thermodynamics, or there's a chapter with the Maxwell's demon and information theory
Yeah.
also. Yeah.
And you're right that I do appreciate history as well. I think they should teach more of history in physics degrees because I think there's too much of an impression that the structure produced in 1930s Germany is perfect. And although it's very good, I I think it would be good for students to see that in the past, every so often people think that physics is perfect. They have thought it was perfect for many millennia, but of course it never is.
Mhm. Yeah, nothing is more destructive at the very end for science than the wrong, false belief in that we have already understood something we haven't. So yeah. So coming back to inertia, if you want to, um, I guess we should then show one central formula of yours, which could be,
Yeah, sure.
you correct me, but I would say that that's the essence of what you have to say, or at least your theoretical thoughts start from. It's the usual and the inertial mass being different. That's of course very heterodox, but also an intriguing thought. And the relation would be like this. It's a dimensionless factor, 1 minus 2c over theta a, and theta is the horizon of the universe, a is the acceleration, and oh well, 2c squared. So that's interesting. I pondered over this, but maybe you want to explain how, I mean, a little bit what's the background is, how you came up with this, or how you dare to consider that inertial and gravitating mass was different.
Yes. Well, it all comes from the waves, because if you have this model that I talked about, where something's accelerating to the right and a horizon forms to the left, then waves are damped on the left by the horizon. But there's another effect as well. There's a cosmic horizon, which is not asymmetrical like the Rindle horizon that I've been talking about. It's symmetrical all the way around.
Okay, let me just think about. So the Rindle horizon would be related to the acceleration. That means if you accelerated, say, to the left, then obviously information from the right cannot reach you any longer because you're getting too fast.
Yep.
So this would be a shift of the horizon. Maybe you get on the other side, another piece of the universe, but you say the Rindle horizon is asymmetric, right? Shifted in the direction of the acceleration. Whereas your concept is different, is symmetric, you said.
Yes, so the new addition is the cosmic horizon, which is the limit to what we can see, which is like a shell surrounding the accelerating object.
But the usual horizon in cosmology, just.
Yes, that's right. So that is also a horizon, and if the object is accelerating very slowly, then the under waves are long enough that they will start to be damped by this cosmic horizon as well. But what that means is that this effect that I'm proposing of the asymmetry in the waves on either side of the object is reduced, because all the waves are slightly weaker than before. So this means that as acceleration goes down, the inertial mass goes down in a new way that you can calculate from the geometry of it. So that leads to the formula that the inertial mass is the original mass times a factor 1 minus a new term, which has the acceleration on the bottom. So as the acceleration gets bigger, the reduction of inertial mass increases.
Yeah, I noticed that because it's something like always brings you back to the balance. I mean, you stop having an acceleration, which usually you don't have. I mean, you're always somehow accelerated, you imagine, but then let's say you're zero or very small for a small period of time, and then immediately that denominator decreases, and then the fraction increases, of course, and then you get much less inertial mass, which in turn leads you to an acceleration because the force doesn't change that mass, and if you're becoming less inert, so you're more prone to be accelerated. So that's kind of a balance that. And I mean, if you do the calculation, I think you derive also then the extra force, which is, let's say, kind of observed as dark matter, right? And you get an extra term, which is roughly c squared over r, or c of the c over the time of the universe equivalently. And then that's the mysterious acceleration of 10 to the minus 10 meters 10 meters per second squared, which we observe, or at least that's the realm of the anomaly, which is usually called dark matter. So it's certainly intriguing that you relate that acceleration to it. Yes.
And it turns up everywhere as well, in wide binary stars as well.
Yeah. I mean, we know that there is a couple of observations. I guess the most serious, undoubtable, and long verified observation is, of course, the rotation curves of galaxies. Vera Rubin already in the 1960s, and there is really no doubt about that anomaly. And then if you look at the small accelerations, you see these anomalies everywhere. I mean, you see it in the clusters, you see it in the stellar in the globular clusters, you see it in the motion of galaxies, you see it everywhere.
Even in Proxima Centauri, our nearest neighbor in space, Proxima Centauri, has the same anomaly.
Yeah, I think that's one big accomplishment of Milgrom. I guess he was the first guy who pointed to the fact that there is a problem with small accelerations, not with so much with huge distances or what you might suspect, that if you doubt the law of Newton's law of gravity. But I think that's his big accomplishment, right? So, yeah.
That's right. So he proposed modified Newtonian dynamics.
Yeah. Which has, let's say, I mean, there are at least graphs which pretty much seems to be successful in predicting galaxy rotation curves. I mean, what are the differences between your way of explaining and MoND, or the parallels? Or I mean, you both dealing with the lower acceleration regime. That's clear. But
That's right. So Milgrom wasn't sure whether it was a change in gravity or inertia. So obviously I decided that it was a change in inertia because nobody understands inertia. It was a big problem. So I thought the two were linked. Also, whereas Milgrom has a constant that he has to fit, which is called A naught, I have a model that is more mechanistic. So I have a reason, a mechanistic reason for predicting this, and I predict that constant.
okay, yeah. I mean, basically, you have also or not, because that's precisely that 2c squared over the diameter. But it's true that you have you try to give a reason for that. That's true. On the other hand, I would say a difference would be, I mean, if I understood correctly, you're kind of adding that acceleration to the Newtonian acceleration, whereas I guess I might be mistaken, but I think MoND is like taking the geometric mean of that acceleration A naught and the usual one. So it takes the usual acceleration times A naught and then the square root. And that would be a little bit different from adding that acceleration as you do, right?
Well, I've shown you can derive simple MoND from quantized inertia, which is the name my theory. So it is. So for galaxies in the present epoch, the predictions are very similar, but the difference with what I'm proposing is that the constant A naught changes in time. So a good test is to look back in the past at galaxies very far away in the early universe.
Yeah. Okay, right. I agree. It's, by the way, an argument I had with Simon White once I described in my book. Yeah, but I guess as a matter of fact, the data we have from galaxies are pretty close, because I mean, from distant galaxies it's hard to get a reasonable spectrum, reasonable rotation curve.
That's true, but they're now starting to do it, and the prediction of quantized inertia is that they should spin more rapidly for the same mass, and they seem to. There's a paper by Genzel et al., which I think it came out
The
in.
one with the Nobel Prize 2020, Gensel. Yeah.
Yes. I didn't know he'd won a Nobel actually, but yes, it's
Yeah. He co-discovered the Milky Way, the S2 star orbiting the center of the Milky Way, and determine what they call the black hole mass. I mean, that's a wonderful observation. let's leave aside all the theory.
I was quite disappointed though, because I submitted a paper to Nature. I occasionally submit papers to Nature just to see if I can do it, you know. And I made this prediction that galaxies in the past should spin more rapidly for the same mass, and they rejected my paper. But then 2 months later, they published Genzel's paper, which showed this observation that galaxies spin faster.
Yeah, I wasn't aware of that. Yeah. Okay. At least it's a prediction. It's predictive. Yeah.
I published it elsewhere, so.
Okay. Yeah. Anything else? I mean, I question another question. You can continue if you want to add something, or should I?
Well, I just say I suppose that the difference between quantized inertia and MoND is that there's a mechanistic model in there, which makes sense. So it predicts this constant A naught. It has predictions that are different far back in the past, so that can be tested. But also, it's far more versatile because you can apply it to experiments in the laboratory.
Yes. I see the point. I mean, that's because MoND, it's simply, I mean, it's just descriptive, and I mean, people would even admit that, I guess. Yeah, that I have no idea how that strange theory could be justified. Whereas you, I mean, pondered a lot over these elementary issues. That's correct. Yeah. So there would be also something which makes us better understand quantum effects or quantum phenomena, you think?
Well, I've already mentioned my studies of time and the EPR paradox and Bell tests, that sort of thing. But that's not quantized inertia. That's a different thing. You can with quantized inertia. I realized eventually that I could derive it from Heisenberg's uncertainty principle, and then so I could derive inertia from Heisenberg's uncertainty principle, and then classical gravity as well. So the Newtonian gravity, not the full general relativistic one yet. So that I was quite excited to do that because Newton's gravity formula just dropped out of Heisenberg's uncertainty principle.
Yeah. I mean, everything is related to that. I think that's a very nice aspect, that everything is related to waves. The idea of this quantum vacuum, and then that's already a link to fundamental physics on the micro scale, right? Even I should say that I mean, I'm very skeptic of all the predictions of quantum electrodynamics, and I think Oliver Conzer did a magnificent job of tearing apart, shredding these manipulations and of measurements of quantum electrodynamics. But still, I guess the idea behind that photons have very much to do with the electron-positron pairs, and then you can imagine one thing as just another form of the other. That's very valuable, that there is something deep in there, and there is certainly something deep in there if you imagine space-time filled with these fluctuations. I mean, the Casimir effect is also real, okay? So yeah, I just wanted to mention this because if we talk about quantum electrodynamics, I have my reservations based on that work of Oliver Conser, but also I myself had the reservations before. But still, the idea is valuable. So, and I mean that's where you're also building on, right? So you're not
Yes.
you're not talking about the anomalous magnetic momentum of the electron, but you're talking about Casimir effect and waves and the quantum vacuum, right?
Yes, I would love to apply to particle masses and try to work them out. I read a very interesting paper by Jennison from 1980 or something like that, where he attributed the electron to a trapped photon, and he was able to get some of the behavior of the electron from
The idea that the electron is a trapped photon.
yes, trapped between
Okay.
mirrors,
Yeah. Yeah.
trapped with the photon.
Yeah. A number of people have followed on that idea, which is certainly intriguing. Yeah. Or I mean, or just try to explain the elementary particles somehow. There has to be a wave. They have to be somehow related to particles. Yeah. I guess that's a good idea as a matter of principle. Yeah.
Maybe I think it may be possible to get from quantized inertia to particle masses, but that's something I'm working on at the moment.
Yeah, again, that's what I like. I mean, you see the physicist interested in the big questions. You're not the narrow specialist, and that's I guess this is what we don't have nowadays, this culture of overview of fundamental physics. I still have one more specific question about your formula with the factor of the quantum of the inertia of the inertial mass. I mean that 1 minus 2c squared over theta a, does that refer to, should I imagine celestial bodies undergoing that acceleration? Because we have the absolute acceleration here, right? The modulus. Should I imagine celestial bodies, or could I also imagine, well, the microscale, the electrons and neutrons
Yes, I
on
think
Earth, or because it could make kind of a difference, because as a whole, you might see the celestial body unaccelerated or with very small accelerations. But on the other hand, you have all these elementary particles which might undergo huge accelerations at the same time. So how should I imagine that?
so. It's quite subtle because in quantized inertia, the acceleration that's used is the mutual acceleration between the object and the object that it's interacting with, that it's seeing a force from. So for the interaction, there will be a different inertial mass, which is different from standard physics, of course. And it's far more complicated if you try to work it out. But that, if you work out the consequences of that, you'll see that the star, which has a plasma at very high accelerations in it, all those accelerations will cancel out, and you'll just have the acceleration left of the star as a whole.
Okay. So if you talk about canceling out, that would, I mean, that would more support the idea of considering the celestial body, which at the end you want to explain the anomaly, right? Okay. Yeah. Yeah, it's intriguing. I like it, and you also, I mean, we also agree that these riddles have to be explained, such as Dirac's large numbers. You mentioned also these, and you mentioned the gravitational constant, which is of course something.
So quantized inertia gives us a way to get rid of G. I know you've talked about this in your books. Schrödinger, Sciama, Dirac, other people have pointed out that there's a relation between G and cosmological parameters.
Yeah, actually, I guess the very first one was Erwin Schrödinger in 1925. He had a paper out there speculating about the gravitational potential of the entire universe being of the order of c squared, and that's what
Yes.
essentially this formula. Yeah.
But quantized inertia enables you to derive this very simply. Because if you appreciate that in a particular volume, you have accelerations high enough, the under waves that are seen are smaller than the if the
I saw the formula. At the end, you're giving the approximation of something like it's kind of 2c squared, radius of the universe divided by mass of the universe. Is this just all the mass and the radius, or is there a sum in there in the formula, like in Sharma's approach? I mean, if we're talking about orders of magnitude, it doesn't make a difference if you put the entire mass and the radius. But if you're looking, say, for tiny variations of local variations of the gravitational constant, you would prefer to write it with the sum, say, sum over all masses divided by the respective radius.
Well, the way I did it, I took the entire mass of the cosmos as an estimation. The thing that interests me is that this explains why that relation seems to be true. I mean, as you say in one of your books, the fact that it is true is fantastic, is amazing. But quantized inertia predicts that it must be true. Yes, the mass in any volume has to increase, such that the gravitational acceleration is big enough so the waves shrink less than the size of that volume. And if you assume that, which must be in quantized inertia, you get that relation.
So you would also assume that in cosmology, you would have a decreasing gravitational constant and a decreasing speed of light during the evolution of the universe.
Well, yes, I haven't worked it out yet. I don't know, because there are so many things that vary.
Yeah, you said that there will be another book about cosmology. Yeah, I shall be curious.
But yeah, I'd like to look at that, because the speed of light might vary, the mass varies as it grows, and obviously the diameter does. But the other great thing about quantized inertia is that if you take the cosmic diameter and you shrink it in a lab using a cavity, then the theory predicts you will get thrust and energy. Two kinds of thrust and energy, which is what DARPA funded me for to try and demonstrate. And we have seen thrust in several labs using capacitors. Faster approach being pioneered by Becker and Batts, and also an American company called IVO, who launched a quantized inertia thruster into space last year.
Yeah, I admit that I'm kind of ignorant of these technical details of this experimental stuff, but it's certainly interesting. And as a method, I agree very much, because I mean, if you do a revolution in physics, a real one that has to change the world in the sense there is a real impact, not just fantasies like supergravity or whatever. I mean, with all the neutrino colors, in theory, we still don't have one reasonable application of neutrino physics, save that. So, I mean,
it's important that a good physicist should not particularly try to have applications, but I think you're on the right path if applications
yes. Not necessarily you have always to deal with, but at the very end, if there is something, then you get something out. I mean, there is no fundamental physics discovery, that's at least my view, that hasn't been sooner or later transformed into useful technology. Whereas I still don't see the useful technology coming out of the W bosons and Higgs bosons and whatever. That's maybe one little thing I disagree with you, because you happen to you have a beautiful list of anomalies in your book also, but you refer also to some anomalies of CERN, of particle physics, and I just think that's a mess anyway. I mean, that's not even wrong in the words of Wolfgang Pauli.
the Higgs fake, which I really enjoyed as well. Very irreverent.
Mhm. Yeah. Yeah, for the rest, I think your book is also valuable from gives also a valuable overview from over the experiments. I discovered something new. I didn't know about about several anomalies, like the GPS was I found one of the most impressive ones.
Yes, that's interesting, isn't it? It's the same as old acceleration.
You said it's GPS satellites undergo an anomalous acceleration of something like 7 times 10 to the minus 10 meters per second squared. But wouldn't that be a huge deviation? I mean, if you integrate that over just a day, I did the calculation before, because you have a times t squared, 1/2 a times t squared gives you the extra distance, and t squared becomes large because 1 day is almost 100,000 seconds. So you almost compensate for the 10 to the 10 by squaring 10 to the 5. So do they just gloss over or correct, or isn't the deviation not that much? I suspect my calculation was maybe too simplified. Yeah.
Not that much. It's the acceleration of 10 to the minus 10 meters per second, so it's quite small. It's very small. But this was work done by Zebart that I saw, and it's very interesting. But he never went back to it. And at one point, I tried to get GPS data, but it's not really available. There are security issues around it. So
You can imagine nowadays that
yeah,
GPS data is something. Yeah.
so it's hard to study that.
Yeah. I see the point. That's a pity because I mean, I always say that scientific data must be public, must be accessible to everyone. You need the routines, transparent, repeatable for the non-specialist. That's what I mean. A particular failure, I guess, of the big accelerators like CERN, that they don't manage their data to make them transparent or somehow accessible. Yeah, but I regret that that's also the case with GPS data. But on the other hand, we have, I guess, public data. You could read the continental drift, for instance, from public GPS stations, but not, yeah, that doesn't affect the satellites. It's just the GPS stations on Earth, they make it public, but the satellites are a very sensitive thing, I guess. Yeah.
Yeah. Well, that's one of the things I used to teach as well, GPS positioning at
Mm.
Plymouth.
Mm-hmm.
That's how I know about that one.
Mm-hmm. Yeah, great to get this impression from your work. You want anything else you want to add, or you want to stress, or there are so many.
It's all in my book, Quantized Accelerations, which
Yeah.
is
Yeah,
available.
we want to leave something also for the reader as an incentive. I can recommend it. Yeah.
And I
Um,
also have a Patreon, which
mhm. Yeah.
is One Step to Tower City, that
Yeah.
you can find me at. And I'm on Twitter. I tend to,
Yeah. I will put that in the description. Also, your archive. You have a couple of papers on archive, which are very readable, I guess. Yeah. One last thought. I think this is very nice in your introduction. You said that um, the ancient Greeks were about to discover modern physics, something like with the steam engine, and you described this very nice little tool. And yeah, it went by as a curiosity of, and uh, people were not ready to see the significance of all this back then, and then we fell in a black hole of science history lasting for 1,000 years, dealing with all this complicated astronomy until eventually science restarted in the Middle Age. So, and you said that we're in a similar situation maybe, and that's what I always say. I mean, all these complicated models are modern epicycles. Yeah. So
Yes, exactly. Yeah.
so, and you said that the most overlooked effect as back then was the steam engine. Now it's something like the Casimir effect, right? So,
I think that's crucial. Yeah.
mhm, yeah.
So we need to. I think we need to pay attention. It's very hard fighting all the vested interests and the inertia of the
Mhm.
academic world. But,
Yeah, it's in a bad shape. Yeah, it's worse than the church in many respects than
but I
today.
do get my papers published,
Hmm.
so that's encouraging.
Yeah. Hmm. Yeah.
Because I always make the point that it predicts real data.
Hmm.
So even if they don't quite believe the model, they can't really argue because
Hmm.
I agree very well with the data. So
Hmm.
the data has saved me.
Yeah. 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 Yeah, and you're also right in pointing out that, I mean, the real key is always an anomaly, something strange that
Yeah,
happens.
right.
The key moments are not, Eureka, I discovered something, but oh, that's strange. That's funny. Yeah. Yeah.
That's right.
Yeah,
Yeah,
one anomaly. Yeah,
like
maybe.
data.
Yeah. That I forgot to talk about this. You talk about anomalies, and you talk about coincidences. I think there is a subtle difference. You kind of calling everything anomaly. Things like dark energy, which is a fudge factor, everybody knows. But yes, I would agree that okay, you observe the expansion or whatever. If it is real, or let's say we observe the redshift, and then you deduce in conventional physics, you deduce the expansion, and then you know, oh, there is something wrong with this expansion. You have the strangely accelerated, and that's what I would call an anomaly, right?
Hmm.
That was the famous accelerated expansion. But there is if you are quantitative, you see that the acceleration is almost the same amount as the deceleration, which is expected from Newtonian gravity.
Yeah,
So what we observe is rather the absence of conventional gravity, of the deceleration, yeah, because
empty universe model. Yeah.
huh? And
It,
then that's what I would rather call it a coincidence, because an anomaly is something that says, okay, something is wrong with your model, think about again. A coincidence is a little more, it gives you a quantitative hint towards a new theory. It's already a first step for building something else, right? Would you agree on that?
interesting. Yeah. Okay. So yeah, if something agrees with something else, that's also very interesting. Yeah.
Yeah, Weber and Kirchhoff noting that the speed of light is related to the electric and magnetic constants. That's quite an
Hmm.
intriguing coincidence, or yeah, uh, coincidences of Johann Jakob Balmer. Yeah, they're just, I mean, yeah, these are the exciting things of physics, and yeah, I guess we at least we agree insofar that going to this small acceleration regime, there is something very interesting underneath. Yeah.
I'm very sympathetic towards the empty universe model. I
Mhm.
haven't written a paper on it yet, but I suspect that the universe is not actually expanding,
Mhm.
but that the redshift is from galaxies so
Mhm.
far away
Mhm.
that the universe is getting smaller, so the physics was slightly different.
You're mentioning also Halton ops, yeah. Yeah, well, what I think is a reasonable extension of the variable speed of light stuff of Einstein and Dicke is that it's just Dicke's idea that there is just redshift is just there's just expansion of light, but no material expansion. Yeah, I think that's a key idea. Yeah, maybe you will agree when you finished your cosmology book or not. I don't know.
It seems
Yeah,
far more efficient. Instead of having 10 to the power 53 kilograms of mass being accelerated,
mm-hmm.
which requires ridiculous amounts of energy,
Mm-hmm.
we can just have it nicely static.
Mm-hmm. Yeah,
So
yeah, that's the beautiful simplicity in Dicke's idea, I guess, of this. Yeah, but this talk today shouldn't be about variable speed of light and my stuff. It was about your quantized inertia. Okay, yeah, thank you so much, Mike, for being here. And I'm looking forward to your further research and maybe further discussions. Okay.
Yeah. Okay.
Goodbye. Thank you.